Hello everyone, welcome to my channel Dr. Tapati's presentation. Myself Dr. Tapati Vanjade. I have started discussion on enzyme kinetics. Before you know in detail about the enzyme kinetics, you should know different orders of chemical reactions. In my last video, I have discussed on zero order reaction. Today, in this video, I am going to discuss about the first order reaction. You will know about expression of the first order reaction, graphical representation of first order reaction, half-life of a first order reaction, examples of first order reaction, and then you will know order of enzyme catalyzed reaction. Let's start the presentation on first order reaction. Reaction proceeds at a rate directly proportional to concentration of a reactant is called a first order reaction. In first order reaction rate is directly proportional to concentration of the reactant. In a monomolecular reaction, if S is substrate and P is product, in this case, the rate of formation of product is proportional to concentration of the substrate, that is S. Let's see how we can express first order reaction. In a chemical or biochemical reaction, when the reaction rate depends on the first power, that will be 1, first power of concentration of a single reactant or substrate is called first order reaction. When the reaction rate depends on first power of concentration of a single reactant or substrate, that is called first order reaction. If S is converted to P product, then the first order rate equation is given by minus ds by dt equal to K into S to the power 1. 1 for first order reaction. Power of S, already told that power of substrate concentration is 1. So for first order reaction, this is the equation for reaction rate, that is minus ds by dt is equal to K into S to the power 1. I am giving this equation as fifth, giving the name for this equation as fifth because we found total 4 equations in my last video. It was on zero order reaction, in case of fifth this equation, in case of this equation, ds by dt is equal to, or minus ds by dt is equal to rate of decrease of substrate, and K is equal to rate constant of a first order reaction per unit time. K is rate constant and ds by dt or minus ds by dt is decrease of rate of the reaction. Why decrease of rate of the reaction? Because we are expressing it as a ds, that is substrate. In a biochemical reaction, with the time respect, substrate concentration is decreased and product concentration is increased. Therefore, it is rate of decrease of substrate. We can rearrange equation 5 to ds by s equal to minus k dt. Now, if we integrate both sides, we will get this equation, or we can convert this equation to this one. As we know, if we integrate 1 by x, we will find ln x. So we can convert this equation into this. Ln st, upper limit is st, minus ln s0, that is lower limit, equal to minus kt, where substrate concentration at time t, it is st, whereas for substrate concentration S0, that is initial concentration of the substrate, the time was 0. I am giving this equation as sixth equation. Again I am writing that equation ln st minus ln s0 is equal to minus kt. That was sixth number of equation. Raising each side of the equation to a exponent e, because we know that e to the power ln x is equal to x. The equation is then transferred as follows: e to the power ln st. If we give e value here, then it will convert it. It will be converted to, if we give e value there, then it will convert it to this one, this equation. E to the power ln st is equal to e to the power ln s0 minus kt. Or we can write it as st is equal to s0 into e to the power minus kt, because already I told that e to the power ln x is equal to x. So e to the power ln st is equal to st, and e to the power ln s0 minus kt is equal to s0 e to the power minus kt. I am giving this equation's name as 7. So equation 7 is the integrated form of first order reaction. That is st is equal to s0 into e to the power minus kt. You have to remember it, very important for mathematical calculation. I have already shown that this is equation 6. ln st minus ln s0 is equal to minus kt, or we can write it as log e base st divided by s0 equal to minus kt. Or it can be written as this: log e base s0 divided by st is equal to kt. Or it can be converted to 2.303 into log 10 base. Here base is 10, and in this case base is e. 2.303 log 10 base s0 by st equal to minus kt, because ln x or log e base x is equal to 2.303 into log x. Here we have done the conversion of log e base to log 10 or ln to log. So 2.303 into log 10 base S0 divided by St is equal to Kt. Or we can write it in this way also. Log 10 base S0 divided by St is equal to Kt divided by 2.303. This is equation 8 because already we have equation 7, that was St equal to S0 e to the power minus Kt. Let's see graphical representations of first order reaction. First graph is regarding the concentration of the substrate versus time graph. Concentration of the substrate, that is S versus concentration of S versus T graph. T is time graph for first order reaction. As you know, equation 7 was St is equal to minus S0 e to the power minus Kt. If you find this equation, follow this equation, we can get this type of graph. First order reactions show an exponential decay of reactant. This is the graph for exponential decay. From this equation 7 we can draw this graph. In exponential decay, the quantity decreases very rapidly at first and then slowly the rate change decreases over time, but the rate of change becomes slower as time passes. Now see this graph. It is ln versus time graph. As equation 6 is ln St minus ln S0 equal to minus Kt. So we can write it in this way also. Ln St minus Kt plus ln S0, and I am giving this equation as 9th equation. It is similar to that of a straight line. Y is equal to m x plus c, where m is slope of the straight line. In this case, slope of the straight line is minus kt. According to equation 9, y-intercept is ln S0. Y-intercept, that is c ln S0. This is the point. Y-intercept is equal to ln S0. Hence, for a first order reaction, plotting ln S with respect to time gives a straight line with the slope minus k. This form implies that a plot of the natural logarithm of the concentration is a linear function of the time. ln S is a linear function of the time. Let's calculate half-life of a first order reaction. Half-life or T half of a chemical reaction is the time taken for the initial concentration of the reactant to reach half of its original value, where T is equal to T half and St is equal to S0 by 2, that is half of the initial concentration. If we put these values in equation 7, that is St equal to S0 into e to the power minus kt, we can get S0 divided by 2 equal to S0 e to the power minus t half, or we can write it as e to the power minus k t half is equal to half, or ln e to the power minus k t half is equal to ln half, or minus kt half is equal to ln half, because ln e to the power is x is equal to x, so here ln e to the power minus kt half is equal to minus kt, or we can write it as kt half equal to ln 2, or that can be converted to we can calculate it the t half value from this equation, where t half is equal to ln 2 by k, that is equal to 0.693. Value of ln 2 is 0.693, so t half value is 0.693 divided by k. It is equation 10. This equation indicates that the half-life of the first order reaction is a constant, because this number is constant and k is also rate constant. So t half value is constant. T half value is constant. It is independent of initial substrate concentration, because in this equation there is no value of S, only it is 0.693 divided by k. T half for first order reaction is 0.693 divided by k. This is not the case with other reaction orders. The practical implication of this is that it takes as much time for substrate to decrease from 1 molar to 0.5 molar as it takes for substrate to decrease from 0.1 molar to 0.05 molar concentration, as it is independent of substrate concentration. In addition, the rate constant and the half-life of the first order process are inversely related, as k value is below this division number. It is inversely proportional. T half is proportional to 1 by k, or inversely proportional to k. From equation 10 we can calculate k value also. So k value is equal to 0.693 divided by t half. So rate constant is also inversely proportional to t half. In pharmaceutical field, along with t half value or t 50% value of 10% is also important. T 10% means the time required for degradation of 10% of the substrate. It is important because it represents a reasonable limit of degradation of active ingredients. In that case, we get T 10% is equal to 0.104 divided by K from the equation 7, that is St is equal to S0 e to the power minus Kt. And we can get T 10% as 0.152 into T half value by putting K value as 0.693 divided by T half. This value is 0.693 divided by T half value. So we can get T 10% as 0.152 into T half. So if we know half-life of a reaction, then we can calculate its 10% value in case of first order reaction, that is 0.152 T half. 0.152 into T half. This is the equation 12. I am going to show you different examples of first order reaction. First example of first order chemical reaction is decomposition of sulfuryl chloride SO2Cl2 to SO2 and Cl2. Second example is the hydrolysis of aspirin. Third example is hydrolysis of tertiary butyl bromide. Fourth example is breakdown of ammonium nitrate in aqueous solution. And ethane hydrogenation reaction. These are all examples of first order chemical reaction. Let's know order of enzyme catalyzed reaction. For an enzyme catalyzed reaction, rate is directly proportional to substrate concentration at low substrate concentration. When the concentration of substrate is very low, at that time rate of the reaction will be directly proportional to substrate concentration. Therefore, it is first order reaction at that time. At lower substrate concentration, there will be enough enzymes to catalyze the reaction. Hence, rate of the reaction will be increased with increase in substrate concentration. They are directly proportional. Therefore, rate of the reaction is equal to K into substrate concentration. And order of the reaction with respect to substrate is 1. Because the power of substrate is here in the rate of the reaction. Power of substrate is 1. Hence, it is first order reaction at the time of lower concentration of substrate. When substrate concentration is very high, at that time rate is independent of substrate concentration. At that time it will be zero order reaction because it is independent of substrate concentration. At very high substrate concentration, above the enzyme saturation, all the active sites of enzyme will be fully occupied by the substrate and there will be no more space available for substrate binding. No more enzymes left to catalyze additional substrate. Hence, an increase in substrate concentration will not affect rate of the reaction anymore. Hence, it will be zero order. So, at a lower concentration of substrate, it is first order. At higher concentration of substrate above the enzyme saturation, reaction order will be 0. If we plot initial velocity of an enzyme catalyzed reaction versus substrate concentration graph, we will find this type of graph. Initially, the velocity of the reaction is increased, but after a certain time, there will be no change in velocity if we increase the substrate concentration at the saturation point, enzyme saturation point. So initially it is first order reaction, and after that it is zero order reaction. After enzyme saturation it is zero order reaction. I will discuss about the enzyme kinetics in detail in a separate video. Thank you very much for watching this video. In my next video, I will give you few numerical problems on first order reaction and their solutions. Kindly like, share and subscribe this channel. Don't forget to press the bell icon to get the notification.